What up, my chemistry people? Welcome back once again to the delightful world of redox chemistry. I guess that's what we're doing, right? Yeah. So here's the deal. I looked over some of y'all's homework, and after today's lecture thingy that I got, it's going to be really short. It's not going to be a lot today. We're just going to go over what a half reaction is, and if you did the homework right, which I noticed a lot of people didn't quite jot this part down. This next part, it should have been part of the homework that you already did, but I'm gonna post another video going over the homework because trust me, y'all need to go over this because that homework that I gave you, it was ridiculously long. There were a lot of equations on that. Now here's the thing: the reason I did that is because y'all need to be able to do this like in your sleep, like hands down, eyes closed. Because to move forward at all, you have to be able to do that. That is a skill you must have. It's a fundamental. It's a foundation. So before we can continue anymore, you guys have to have that. So after this video is done, I'm going to be making another homework video. Please tune in and check it out because man, it will help you a lot moving forward, like doing what we're going to do today, which is half reactions. So sit down, buckle in, and enjoy the ride because here's some knowledge coming right at you, people. All right, today we are doing this. We are looking at half reactions today. All right? But you know what? I don't feel like this is big enough. What do you think? Should it be bigger? I kind of feel like it should be bigger. Yeah. All right. So today we are going to look at half reactions. Now, some people are always asked, they say silly things like, "Hey, what's a half reaction?" Dude, it's it it's half of a redox reaction, man. I mean, the names kind of like are like right there, right? So basically, what a half reaction is it shows us either like half of like it shows us the reduction or the oxidation, like half. You know what I mean? Because redox has two parts: oxidation and reduction. So a lot of people ask, well, why? Why would you want to know what a half reaction is? Well, it turns out that if you have a battery, right? There's like this thing. I think this is the positive end. This is the negative end. Well, inside the battery, you have basically one half of the battery that is positively charged. The other half is negatively charged. And this is step one for taking a chemical reaction and separating it, and which is literally what's happening inside of a battery. We're separating a chemical that's a really bad battery. We're separating dang. We're separating man, I'm just going to get rid of this thing. We shouldn't even have to look at this. We're separating chemical reactions and then we're putting them into a box so that we can like make electricity come out of them. You understand what I'm saying? So that's what a half reaction is. It's just the oxidation, it's just the reduction, and the reason we do that is so that we know like what side's going to be positive when we make a battery, what side is going to be negative when we eventually get to making a battery, which is like the next step after understanding what half reaction is. Believe it or not. And also, not for nothing, but this is like a point that I'm just going to make. I don't know if it's really actually necessary, but for some reason, I often find that it is necessary to say that they can't happen by themselves, guys. You understand what I'm saying? It just can't happen. So, moving right along. Oh, here's a nice little equation. Yeah. So, here we go. All right, what is it? We got copper. Oh, not copper. We have copper 2 plus and zinc. It's starting out as zinc. This is a metal, right? Because it has a 0 charge. And here we have copper with a 2 plus charge. And here we have zinc with a 2 plus. Oh, and here copper goes to 0. So first thing we're going to do is write the change in oxidation state. And what I had you guys do for the homework before is we're going to take and draw lines connecting things. Right? So what I'm going to do is we're going to write the change in oxidation state, which is what we needed to do for the homework. Right? So for this one, I would write zinc 0 turns into zinc 2 plus. Easy peasy. Lemon squeezy. Now I'm going to connect copper and copper 0, and then I just write it down. I'm going to write copper 2 plus turns into copper 0. You guys get what I'm saying? That is step one for writing a half reaction. Let's double check. Let's see how much knowledge we retained, how much learning there is. This is going from 0 to +2. Is that reducing? that is, the charge is definitely not being reduced, so I'm going to call this oxidation. And here, the copper is going from a +2 to a 0. The charge is definitely being reduced. I'm going to call that reduction. And I'm going to call this, so if this is being oxidized, this is the reducing agent. And if this is being reduced, it is the oxidizing agent. Right? Because the thing goes like this. Zinc was oxidized. Who is zinc oxidized by? Zinc was oxidized by copper 2+. That makes copper 2+ the oxidizing agent. Right? Same thing, only different with the other. Okay, moving on. Next thing we need to do is we're going to add electrons to the half reactions to balance the charge. Right? That is the only thing we're going to be doing. We are going to balance the charge. And if you remember, electrons have a charge of -1. So here's how this will do. Here I've got zinc. Zinc 0 is going to turn into 2+. So the question is, what side do we have to add electrons to make the charge on each side 0? Because remember, we have to honor conservation of charge. That was in the very first day of the notes, like way up top there. Because charge comes from particles, from electrons, and they don't magically appear or disappear. So when we have a half reaction, or really any reaction for that matter, the charge that you start with has to be equal to the charge that you end with. That's just how it's going to go. Do you guys understand? So from beginning to end, it has to be equal. Okay? Okay. All right, so electrons are negative. Well, the charge goes from 0 to 2+, so I know I'll need 2 electrons because there's 2 charges changing. And I'm going to try to put them here. And then I'm going to check myself. I'm going to see what we'll check it. So on this side, if I add up all the charge, I have 2 times 1, that's -2. And here I have 0. Then over here I have just 2+. All right, so that tells me that 2- and 2+, these are not equal to each other. So this is not right, right? So I am wrong. I am wrong. And that's how I can tell. You should never get half reactions incorrect because you could just add up the charges to find out. Do you know what I'm saying? So if this side was wrong, let's try this side. I'm going to add 2 electrons to this side. And now let's go double check the charge. Over here, I have a charge of 0. On the product side, I've got 1 zinc with a 2+, so I have 2+ in all. I have 2 electrons. Each electron has a charge of -1. That gives me a total of -2 in all. So I have +2, I have -2. Oh, look, 0 equals 0. I'm right. I win. Yay, because I checked my work. You guys see how that works? So we're adding electrons not to make it like 0, not necessarily to make it 0, but to make the charge equal from reactant to product. Got it? Great. I know you do. Let's keep going. So let's dig into some half reactions. You wanna? I knew you would. All right, first things first. Can't do this unless I know the oxidation numbers, which is why I had to do that ridiculously ungodly long homework. So let's just check it out. Iron, this is an element, it is 0. This is oxygen, it is a 0 here. Oh boy. All right. So let's go to the cosmic freak out brainy stuff. All right. So this is another little thing. These coefficients have nothing to do with oxidation numbers. They just tell us how many molecules are there, right? It has nothing to do with the individual atoms. So I'm going to ignore these as I find the oxidation number. A couple people actually asked that question because some people are brilliant enough to ask. Love you guys when you do that. So let's do this. If I look at my periodic table, the elements, iron, yeah, turns out iron can be like either a +2 or a +3. So I don't know what that's going to be. So let's check it out. There are 2 irons. There are 3 oxygens. Iron is an I don't know. Oxygen is a -2. Now when we do the thinky thinks, 2 irons. Each iron has a charge of X. That'll give me a total of 2X. I have 3 oxygens. Each oxygen has a charge of -2. That gives me a total charge of -6 in all. These all add up to 0 because there's no charge. It's a neutral compound. So 2x minus 6 equals 2x equals 6. X equals 3. And let's get rid of our cosmic thinky thinks here. Another shortcut, guys, that you can often use. I'm just going to throw this out now. Like, you see this 3? The subscript, it's like the opposite of the crossover. It's the opposite of the drop and flop. You can quite often take the subscript and move it up into the charge. Take the subscript, move it up in the charge. But I didn't tell you that, so, you know, don't look at me. All right, so here we go. We have iron goes from 0 to +3. And oxygen goes from 0 to -2, 0 to +3. So it looks like oxygen is getting reduced because the charge is going down. So the oxidation will be iron 0 turns into iron 3+. Now, how many electrons do I need to add to make this equal on both sides? 3. Right? And I'm going to put them over here because my charge over here is 0. So I've got a +3 here from this iron ion. And now I will have 3- from 3 electrons, each with a charge of -1. That'll give me a -3 in all. Equal 0, 0. Nice. And so for my reduction, I'm going to start with oxygen 0. Oh yeah, and also, by the way, I don't know if you noticed, I'm doing this one atom at a time. I don't care about the subscripts. I don't care about the coefficients. We're looking at what happens to each individual atom one at a time, because that's what's happening. It's just the redox, just the oxidation, just the reduction. We're not going to complicate it with coefficients and subscripts and all that kind of stuff yet. But hold on tight because it's coming soon. All right, so oxygen goes from 0 to oxygen -2. Now, where could I possibly put electrons to make this nice and, remember, equal? So here I have 0. Here I have a -2. Well, if I put electrons over here, man, that's going to make it more minus, more negative. That is not what I want to do. So I'm going to put 2 electrons right here. That way I'll have 2 electrons, each with a total charge of -1. That gives me a total charge of -2 in all. And over here, I have charge my, man, this is easy. This is easy. I can do this. I can, this is stupid. Why are we even doing this? Element 0, element 0. Man, I'm used to crossover here. I guarantee this is a +3. Because chlorine is always a -1. There's a couple ways I just thought through this. One, I saw there was a subscript. I did the reverse crossover method thing. And so instead it took that subscript, made it a charge. Took that subscript, made it a charge. Also, the other way we do it is if you just think it through this way, the chlorine is over here. So it's always going to be a -1 because that's the only thing it could possibly ever be when it's negative. So if each chlorine has a charge of -1, and there are 3 chlorines in all, how much negative charge is there? Well, there's going to be -3 in all, which means that iron has to be +3. You dig what I'm saying? That's how kind of how I do it. And so, you know, we're gonna do the same old. Iron goes from 0 to +3. Chlorine goes from 0 to -1. I think I'm going to do the reduction first because that's what my eyes see easiest. I can see that chlorine goes from 0 to -1. I see that that's lowering, reducing. So here's my reduction half. I'm going to do chlorine 0 turns into chlorine -1. How many electrons? What side? Well, the difference in charge is 1, so I'll need 1 electron, and I'm going to put it right here. That gives me -1 on that side, -1 on that side. Easy peasy, lemon squeezy. That means the oxidation must be iron 0 becoming iron 3+. Now I'm going to have to ask myself, what side do I put the electrons on? How many? Well, it's oxidation, so it's probably going to be over here. And I'm going to need 3 of them. Right? Because if I'm going from 0 to plus 3, this side is more negative, or I'm sorry, more positive, so I got to smoosh it down to make it equal to 0 by adding 3 electrons. Now, I don't know if you've noticed a pattern here. I hope you did. Oxidation, it's always right here. The electrons are always being lost, right? Because they're starting in, the electrons are in, they're in the iron here, and then they popped out, losing electrons. So for an oxidation half reaction, the electrons will always be on the right. Same thing, except completely opposite. With reduction, these electrons are always going to be on the left because definition, remember Leo says Ger, it's gaining electrons. They're being added together. Here you see the electrons, and there you see an oxygen atom, and there, the electrons are gobbled up. They are in that atom now. They're a part of the atom. Ion. Technically, it's an ion. It was an atom, but now it's an ion. Don't. So, now let's look at this other oxidation and reduction. Oh my gosh, oxidation, look, the electrons are on the right. Reduction, electrons are on the left. Weird. It's like a pattern that happens like a lot. All right, let's look at this last one because look, we have a special word here, spectator ion. Now let's do this. You know what I'm gonna do? I'm gonna do this backwards. We're gonna talk. I'm gonna give you the definition of a spectator ion, and then and then I want you to like see it in action. So the NO3 in this case is going to be the spectator ion because it doesn't do anything. I want you to kind of clue in on that. Like it just sits there, and we just ignore them in a half reaction because they're not oxidizing, they're not reducing. Right? You got it? So spectator ions don't change at all. So let's dig in here. All right, let's get our oxidation numbers on first. All right, element easy. Silver, it's a +1 because periodic table of the elements, it's going to be a +1. NO3 is definitely going to be a -1. Do you know how I know that? Because I looked it up in the reference charts, because you should be doing this with your reference charts right there next to you. It's crazy not to. Moving right over here. Copper. Well, copper has 2 choices, but I don't want to do that homework thing. I know that each NO3 is a -1. I have 2 NO3s. How much negative charge do I have in all? Well, in all, I have -2. So to cancel that out, this copper must be a +2. Right? And so NO3, if I go to my reference table, I can see that my polyatomic ion NO3 has a charge of -1. And this silver is an element, so it's going to be 0. And now I'm going to draw the connecting lines, although I think we already know which ones these are going to be. And I want to point out with my rainbow pen here, you see NO3 -1, NO3 -1. It's no change, right? No change at all. It starts out as a -1, and it's going to end as a -1. That's what makes this the spectator ion, because nothing happens. Do you guys get what I'm saying? Nothing happens. So let's go. Oxidation. Copper goes from 0 to +2. That's got to be oxidation. So 0 is going to turn into, because oxidation is losing electrons, so it's losing negative charge, and I need two electrons, right? So +2 -2 is 0, 0 on that side. Everything is spectacular. Now let's look at reduction. Silver is going from a +1 on the reactant side, and on the product side, look, we have silver 0, elemental silver. So if I've got a +1 on the reactant, 0 on the product, I know I'm going to need 1 electron here. -1 + 1 is 0, 0 on that side. Bam! Just like that. Oh, I think I already did that. Yay, we're done. That was it. Guys, seriously, that's it for today. All we have for you is this, writing half reactions. We're literally, I want you to do this. That's it. Find the oxidation numbers, draw the lines to connect the things that change, and then just write them out, just like you were supposed to do on the other homework. And then you add electrons to each side to make the charge equal. It may not always be 0, because remember, these things are like the easy sample problems. But that's all I got for you today. Tune in. I'm going to go over that homework for y'all. Hope you guys have a great weekend. Oh, also, not for nothing, man. This weekend is supposed to be beautiful. So listen, I'm going to tell you right now, man. As soon as I'm done uploading this video, I'm going to post the answer key at midnight, because I am not, man, I'm outside this weekend. I recommend you do the same. So get it in by midnight so we can have the weekend off. Hope you guys have a fantastic day of knowledge and learning. Happy Coronication.